This is an introduction to solving systems of equations in two variables. Let's start by going back and thinking about the things that we've already done. Okay, solving an equation, or just what an equation looks like. Let's say that's a line, which it is, and it's got a slope of about 2, and let's say the intercept's right there and it's 5. So this would be what? It would be the slope y equals 2x plus 5. Every point on this line, if you substitute it in to the equation, you'll get something that's true. So for example, if this equation is y equals 2x plus 5, you plug in 1, 7, substitute in the 1 for x, the 7 for y, you will get 7 equals 7, and it'll be true. You substitute in 2 and 9, you'll get 9 equals 9, it'll be true. Negative 1 for x, 3 for y, you'll get 3 equals 2 times negative 1 plus 5, which is 3 equals 3. For every point on the line, the equation is true. Okay, you already knew that. What about this one? Okay, let's say that's y equals negative x plus 3, that the intercept is 3. For every point on this blue line, if you substitute it into the equation, you'll get something that's true. Every point is true for the equation for the blue line. Every point is true for the equation for the red line. But this point right here is on both the blue and the red line. It's like it's, you know, purple or something. It's on both lines. So the coordinates of this point, well, if you substitute it into the blue, you'll get that it's true, it's on the blue line. If you substitute it into the red equation, you'll get that it's true, that it's on the red line. This is the only point that that's true about, because two lines intersect in at most one point. Now, they might be parallel and never intersect. Again, we're talking here about this all in the same plane. So there would be no intersection here. We won't talk about that today. And then there are some folks that say if it is at the same place that it's the same line and it always intersects, but we're not talking about that today. We're just talking about this point right here. And you know what? That's like x marks the spot. And this is one of those unusual times when x actually does mark the spot. When we solve a system of equations, what we want to know is this point. That's all we care about. So at this point, the red x is the same as the blue x. The blue y is the same as the red y. For this point, is that true any place else? No, it is not true any place else. But you know what? We don't care, because this point is the only point we care about. We want to know which satisfies both equations. Now, when we get into a whole lot more complicated stuff, we'll start to learn that this can be really useful. Now, here in Algebra 1, we don't really know enough yet to do it, but we can understand that we're getting there. For example, if this is, you're in an ice cream store, and this is the line that represents how much you might charge for your ice cream, different values of prices for your ice cream, and this line might represent an equation that talks about the behavior of your customers as to whether or not they'll pay that much money for and come into your store and buy your ice cream. So there's always a sweet spot where it's the best, the point at which you'll make the most money when both of them are true. Sometimes you make more money by selling things for less because you sell so much more of them that overall you make more money. And sometimes it doesn't work that way. Now, when you're really in business, you'll have a lot more equations, and they'll be a lot more specific than that. But you'll always have these points, these sweet spots, where you can tell what the best option is for whatever it is you're looking for in your business. So they can be helpful, not always, of course, perfect. We're going to learn two ways to talk about how to find out the coordinates of that point. The first one is going to be by graphing. Let's look at that right there. What we just did, but actually on the coordinate plane, doing it a little more specifically than I just did with concepts with my red line and my blue line. Okay, I'll start here. The top one will be my red line, y equals negative x plus 6. Okay, so the intercept is 6. The slope is negative 1, so I'll start at 6. And I'll draw a line with a slope of negative 1. That's down 1 over 1. And I missed a little bit, but you got the idea. Then we'll graph the other one. My blue one here will be y equals x minus 2. Okay, the intercept is negative 2, and the slope is positive 1. So that's going to look like right here. Okay. X marks the spot. X marks the spot. That's really convenient. You know in that Indiana Jones movie where he was looking for something and he was in this big library-like place and he couldn't find the X and he couldn't find the X and it was a 10 and it was an X and he couldn't find it. He looked around, he went up high and he looked down and there was this X. So he went in and busted the floor in and got what he needed. X does sometimes mark the spot. And with systems, X does mark the spot. So this is the point 4, 2. That is the solution to this system. Now sometimes when people are doing this, they think it ought to be harder. Okay, and they'll graph it and they'll say, Miss, I don't know what to do now. I say, there it is, there it is. X marks the spot. Okay, let's try another one. This equation, these two equations, they are not in slope-intercept form, so we'll have to use a different method to graph them. They're close to standard form, so let's treat them like standard form. This one will be my red one. Remember, in standard form, the simplest way to graph is using the intercepts. And the simplest way, cheap and dirty way, to find the intercepts is to cover up. So if you want to know the x-intercept, get rid of y, because if it's not there, it's 0, and 0 is the same as not being there. So just in your mind, solve that. 4x equals negative 12. The x-intercept is negative 3. Okay, so that's going to be right there. The y-intercept. To find the y, cover up the x. Oops. So there we have negative y equals negative 12, so y equals 12, which is, what did I just do? I did that one wrong. I'm sorry. So y equals 12. You probably already caught that. I put it on the wrong axis. There we go. So there's my first equation and my second one. Again, we're going to cover up to find the x-intercept. The x-intercept is negative 3. I'll try to get it in the right place. Oh, look, it's the same. That's going to be easy. The y-intercept is also negative 3. And I draw it. And yes, indeed, x does mark the spot. The solution to this system is negative 3, 0. Let's do another one. So here we have, oh, this is back to slope-intercept form. So I'll start with the intercept. Okay, it's y equals negative 2 plus 1. The intercept is positive 1. The slope is negative 2. Y equals mx plus b. So what I will do then is over 1, down 2, over 1, down 2. Draw my line. Then graph my other one. It's also in slope-intercept form, so I'll start with the intercept, negative 5. And then the slope is 1. It's not there, so it's 1. So it's understood, because 1 times anything is it. Same thing. And again, yes indeed, x does mark the spot. The solution to this system of equations is the point 2, negative 3. Here's some more of them that you can try. Try that one. See what you get. The solution to it is right here. Notice that its units are by 3, but you can still count. Over 1 and up 4, because that's over 3 and up 12, which is the same as 4. It reduces to that. Now we're going to talk about solving systems simultaneously algebraically. First we'll do algebraically. If you would, please write these down in your cipher and we'll talk about them. So pause it and write these down. Then I'll talk about how to do it. First up, we're going to solve this by algebraically. Our two equations that we're going to use are x equals 1 minus y and 2x minus 2 equals y. And let's look at our terms here. First, we're going to isolate one variable. Okay, any one of them, we've got 4 letters here, 4 variables. I'm going to isolate any one of them. It does not matter which one you choose. You will get the same answer. It doesn't matter. So I could choose the x. It's already isolated, so it's like really easy to isolate it. I could choose this y here. It's already isolated, so it's like easy. If I were to choose this x, I'd have to divide everything by 2, and there'd be a half there, and I don't like fractions. So I'm going to choose this x right there. So I'm choosing the x. Okay, remember this x marks the spot stuff? At the point that we want, and it's the only point we want, at that point, this x is exactly the same as that x. This y is exactly the same as that y. But miss, it's only for that point. Right, it's only for that point, but that's the only point we care about. So we look at that, we say, that x in the first equation is the same as that x in the second equation. But this x is the same as 1 minus y. So if this x is the same as 1 minus y, then this x must be the same as 1 minus y, which means I can put in or substitute 1 minus y is I'll rewrite my second equation. 2 and then times all that mess. Okay, now that mess is an expression and it's going to need some parentheses. So I'll write in some parentheses. So that was x, that was x. They're the same because it's the same spot because x marks the spot. And that's the same as both of them. So I just write that in. Then I finish writing my equation. And I look at that and I say to myself, that's a first week of Algebra 1 equation. I can do that. Hey, I even learned that in pre-algebra maybe. So go ahead and solve it out. And what it will look like is this. 2 minus 2 is 0. But you know, a lot of people here, they don't give 0 any credit. They say, Miss, I can't work it. Yes, you can. That's 0. Go ahead and finish isolating your variable, and you get y equals 0. Okay, I know y is 0. The y coordinate of the point that I'm looking for is 0. So now I need to find the x coordinate. That's right here. Substitute. Let's see. I've isolated, I've substituted, I've solved. Now I need to, don't use that. Like, don't use this one. You'll get nonsense. And if you've modified it, don't use that one. Use an original. So here are my originals, and it looks to me like this one's easier. So I'm going to choose the top one to substitute into. Oh, that was hard. X equals 1. So I find my solution is x equals 1. That's how I've done it using substitution. The other way I call columns, because you've got to make columns out of the different the different items. So if you would, please write these down in your cipher. These, to add columns, I talk about it that way, but other folks talk about it as eliminating a variable. And it is true that you do eliminate a variable, but you do up here too. So it's not really distinctive as a title. And column seems to help a lot of kids keep track of what they need to do to be able to solve it. So I'm going to take my same two problems. X equals 1 minus y. 2x minus 2 equals y. It's the same. I got to have my x's on top of my x's, my y's on top of my y's. So what it's got to look like is all of the x's lined up, all of the y's lined up, and the equals gets its own column, and then all the plain old number terms that don't have a variable lined up. Then everything has to be in its own column. When I look at my first equation here, that's not that way. My second one is close. My first one, I can just add y to both sides, and it'll. The second one here, I can subtract y from both sides, and then add 2 to both sides, and what I'll get is 2x minus y equals 2. So I've rearranged each of the equations into what I call columns so that all the x's are on top of the x's, the y's are on top of the y's. The equal gets its own column. That's the mistake most people make. The equal has to always be lined up, and then the plain old numbers on the other side. Essentially in standard form is what we're using here. But things can be negative. We don't care about that. Okay, now I need 0 pairs. Again, what I'm trying to do is get rid of an x or get rid of a y. I want it to go away. Why? Because look up here. When I got rid of one by substitution, life just got really easy peasy. I mean, I could work it, and I mean, look at it. It was nothing. So if I were to be able to either get rid of the x terms altogether or the y terms altogether, that would be really great. So what I need then is a 0 pair. It doesn't matter if it's an x or if it's a y. I need 2 x terms that'll add up to 0, or 2 y terms that'll add up to 0, because that way it'll go away. It'll be like matter and antimatter, and they meet, and poof, they're gone, which makes it really easy to solve. Well, let's look at what happens here, and we notice, oh my goodness, look, there happens to already be a 0 pair. See it right there? Y minus y. Oh, that'll work. That's atomic. So now let's just add our columns. X plus 2x is 3x. That was hard. Y minus y is 0. The equals is still in the equals column, and 1 plus 2. Now to solve this, we have 3x equals 3, not exactly tough, and x equals 1. That's the same thing as we got here. We know that the x value of our equation is 1. If we substitute it back into the equation, we put 1 in there. 1 equals 1 minus 0. We find that y is still 0. Notice that we got the same thing both times. It doesn't matter how you work it, as long as you observe all your appropriate algebra